This webinar is titled Calibrating Force Uncertainties using ASTM E74-18. That's going to be our primary focus and discussion today is going to be on using the method and assuming that people have their instruments calibrated in accordance with ASTM E74. Our template also allows you to use the same principles that we were going to discuss today and do other calibrations for single run or other instrumentation. For those that were on earlier, you just click other in the field and you can enter that in the uncertainty template. To keep the time down, we're just going to discuss the example using ASTM and do a little bit of history as well. So what we do, for those that do not know us, we are a manufacturing company that produces force calibration equipment and adapters that are used in industry to measure force. We have force and torque calibration laboratories and offer calibrations at a very high level of accuracy. On the left is a deadweight primary standard. On the right is our torque primary standard. Torque, we're now claiming about 0.003% of applied torque, second most accurate torsion machine in the world. And we are doing more and more instruments monthly because we're building up our adapters. When we did with the force business, we've been in business since the 1920s, and we've been doing actual force calibration since the 70s. So we've been building up those adapters for well over 40 years. With torque, we started in 2010, and we see different instruments all the time with different adapters. So our capability is expanding to do more and more instrumentation, and we are expanding to go higher and lower, do lower torques as well. So what we're going to discuss today is why we developed the method that I'm talking about to calculate CMCs. I'm going to discuss a general overview of typical force systems and their uncertainties, and I'm going to cover Morehouse recommendations for calculating calibration measurement for force calibrations calibrated to ASTM E74. So why we developed a new method? This current method is being balloted. It's as part of the MAC committee with A2LA. A lot of people have reviewed it, signed off on it. It is still in probably the late draft stages. It's supposed to close in September for any comments in. I know some people that are listening to this or maybe listening to this have contributed, and all those comments were taken, and the majority of them have been implemented. So this method that we're going over today has been reviewed by several people. But why are we doing it? So NCSLI RP12, we have that document, determining and reporting measurement uncertainties. That's in section 7. We have Euromet, excellent document, CG4, uncertainty of force measurement. But the Euromet relies on having the transducer calibrated to the ISO 376 standard, and that is basically the European equivalent to E74. It's not, but it is. I'm just going to leave it at that instead of getting too detailed. And then we have the ASTM E74 appendix. And we really, if you look at all this, we really have a lack of proper guidance document for ASTM that complies with accreditation bodies' requirements for calculating CMC. And I'll go over that as we go through this. Some people may say, hey, you just have the appendix there and that's fine, but the appendix does not meet the international protocols, and it does not, which basically means it does not meet the accreditation body's requirements for calculating CMC. It does not really align itself with the GUM or the Euromet or any other standards. It takes bits and pieces and does things. It probably should be rewritten and re-examined. So if we look at NCSLI RP12, determining and reporting measurement uncertainties, basically NCSLI says, hey, put all this in your budget. Calibration weight or load, great, load cell sensitivity. It says put all this in your uncertainty budget and go do that. And if we do that, we get something like this. This was a budget NRC Canada had put out as available free online, but we get things like this, and this is what we see happening. Someone has their device calibrated in accordance with the ASTM E74 standard, and then they're putting in things like non-linearity. Why is that in there? And we're going to talk about that. And they're not putting in the key component, which is the ASTM lower limit factor. So it was calibrated in accordance with the ASTM E74 standard, and yet no mention of lower limit factor, which is basically the expected performance of that device in the field. It should be in there. It's not an auditor actually, one of our customers, an auditor actually looked at their document and approved this as an uncertainty budget when they were having cals with ASTM, which at that point triggered us to say, wait, something's wrong here, and something's drastically wrong. So we're going over it today. So if we look at this at 2,000 pounds, we had an uncertainty of 1.21 or 0.061%. If we'd look at a full range at 200, it would be 0.61%. So using the previous template for ASTM E74 is just about as valid as flat Earth theory. I don't know how many people have seen it or seen this lately. It's just silliness that there are more and more people that believe in flat Earth. And my comparison is, without the lower limit factor, it's like believing in flat Earth because gravity, with force, we need to correct for gravity. If we had flat Earth, we would have no centrifugal forces applied to objects, so gravity would not be affected by latitude. That means really no gravity. That means no gravity correction required. So if we look at force requires the correction for effects of local gravity, air buoyancy, and material density. There's the formula there. There's our sheet, our measurement uncertainty worksheet that can be downloaded. Here's screen cap of it. The file will be available in PDF for anybody that wants it later. They can get this presentation on PDF. So I was looking for some type of comparison. I'm a big avid movie buff, so I was looking for some type of comparison between uncertainty budgets and how do you really explain uncertainty budgets. I came up with, you know what, they're kind of like movies. To have a really good one or one that's going to win awards, you have to get everything right. You have to have your actors, your writers, your cinematography, your director, editing, makeup, sound, special effects, costume design. And your budgets, some of them may still be passable. If you have some of the things are just okay. Maybe you're not accounting for adapters properly, but the auditor doesn't see it, and you've at least allotted some contribution for it. Or stability, there's several ways to do stability. Maybe you're taking the standard deviation of the last 3 cals when it might be more appropriate to just do one of the points in the range per point in the range. There's different things you can do, but it can turn out okay. But if you miss the important parts of what you're doing, things go badly. Important parts would be missing the lower limit factor, entirely not accounting for stability at all. You have stability from one cal to the other and you just ignore it. Say, hey, I want my accuracy to be 0.1% of full scale, adjust it, it's within. I tell my auditor I'm within 0.1%, here's my repeatability study, and I never show any evidence of stability. I never show that my instrument has drifted out every single calibration. I'm just accounting for, that 0.1% accuracy statement in addition to repeatability. That's a bad one. So, but again, can you imagine, watching, a movie like Braveheart, with people dressed in blue jeans? You get everything else right, but they don't get the costume design, so people are just dressed in modern day attire. Or you have Sylvester's, Beverly Hills Cop with Sylvester Stallone, which he was rumored to be playing that. Or you have, as lousy as some of the budgets are, you have things like me filming Titanic in my bathroom. There's my version of Titanic. It's sunk. There's all the stuff. There's the crown jewel or whatever it is. But yeah, so hopefully that makes some sense and that correlates. But if we look at some of the force standards and compare them to movies, if those familiar or not familiar, Euromet CG4, very, very good standards, like Lord of the Rings, Return of the King to me. It's the movie won an Academy Award, but anyone who's seen it probably knows that it seems to have multiple endings where you think it's done, and then there's more, and then there's more. And Euromet is really that way in that it wants you to account for, if you read it, you gotta have to account for all of these uncertainties, all these things that aren't being accounted for in ASTM E74, and then more on top of that. And it's a guidance document. It's done very, very well. I say that everything in anything that they could think of was probably put into it, and it's 23 pages. We compare that with the other ones I discussed. The ASTM E74 appendix is 7 pages. NCSLI RP12 is 18 pages, but only 5 specifically deal with the load cell. Then amplifiers are added as well as DC voltage. And we have NCSLI RP12. I kind of think that this one's like Fight Club, where the viewer does not know what exactly is happening. It's not as clear to what applies to the actual use in the field. Plus, it cannot be used for calibrations done in accordance with ISO 376, ASTM E74, the Australian standard 2193, and several other standards. So then you have the other one. You have the ASTM appendix. I kind of think it's like a Rocky Horror Picture Show. It's very mixed, with some people praising it and others thinking it needs to be rewritten and aligned more with international protocols. I like Rocky Horror Picture Show. It's one of those movies. It's kind of fun. It's kind of campy, but I'm on the other side with the people that think it needs to be rewritten and aligned with international protocols. Because when you read it, you look at everything, you read the GUM, you read A2A R25, you read all this other stuff. It's clear that ASTM is not aligned with the international protocols, and it kind of sits on its own. And then you have this hybrid approach that we came up with. We take the good parts of the ASTM E74 appendix and combine it with the good parts of A2A R205 specific requirements. Instead of just using a student T or using a coverage factor of 2 to get close to 95, we use the Welch-Satterthwaite equation, so everything's weighted and we can get a true coverage factor for each point in the range. So and that's really more in line with international protocols, and that's what we're going to discuss here today. So you have your typical tiers for force calibration. You have your tier 1 primary standards. Those are dead weights. Uncertainties can vary between 10 to 50 parts per million. Tier 2 is secondary standards, instruments such as load cells, proving rings, and other force measuring devices. Typically, the uncertainties are greater than 50 parts per million and less than 0.05%. And then the next one are your working standards, which usually those are calibrated with calibrated with secondary standards. Though sometimes they're calibrated with primary standards as well. And instruments such as more load cells, force gauges, crane scales, dynamometers, where this may be something where somebody says I need 0.1% of full scale. That would not be an ASTM cal, it would be another cal, but it falls in within that realm. And then you have your tier 4 devices, which are used for verification instruments, universal testing machines for testing material or verification forces, and typically vary 0.5% to 5%. Further dissemination of force is very uncommon because the uncertainties are quite large. So you don't hear of too many people using, hey, I have my universal testing machine and I'm going to use it to calibrate your load cell that you can then go use to calibrate a dynamometer. That really does not happen. It's usually, hey, the deadweight machine calibrated the load cell that's used in a comparator machine, and then that's used to calibrate the dynamometer. And here's how that works. So you have 4 CMCs at different tiers. So tier 1 is to the left. There's a primary standard used to calibrate secondary standards. If we're talking with ASTM, we're talking about verified range of forces, and we're talking a class AA verified range of forces. The picture in the middle is a load cell set up in compression being calibrated in a primary standard machine. Then that load cell gets used to calibrate other load cells. We have a class AA device, or we have a tier 1 calibrated load cell. It gets put in the machine. Tier 2, the secondary standards. Usually we get uncertainties about 0.02% of applied if we use several load cells, and that's what we're going to discuss. And that's used to calibrate other load cells to class A. Now they can also be used, we can go to tier 3, and those load cells can also be used to calibrate working standards using comparators such as there's our bench top where we're doing dynamometers with crane scale modeled tension links, handheld force gauges, different equipment, including on the right we have some testing machine, load cells being used to calibrate testing machines. And then you have CMCs that vary. It depends on what instrument you're calibrating. CMCs, repeatability studies, and the CMCs vary all over the place, typically between 0.03 to 0.5% in this tier. So when we talk about those uncertainties, we talk about what goes into that. So if you're familiar with type A and type B uncertainty contributors, the type A contributors for these type of calibrations typically are ASTM lower limit factor. That's reduced to one standard deviation. Anyone familiar with ASTM standard knows that the lower limit factor is reported with K equals 2.4. We have repeatability of the best existing device, and then we have repeatability and reproducibility between operators, which we will discuss. What to take? Do you take both? Do we just take the reproducibility? A2LAR 205 asks for reproducibility. The other ABs are asking for reproducibility. They're kind of not asking for repeatability and reproducibility both, so you may not need to put both in the budget, just reproducibility. And then you have type B components, resolution of the best existing device, reference standard resolution if applicable. Of course, if you're using primary standards, then you don't have an indicator, you're not going to have resolution. Reference standard uncertainty, reference standard stability, environmental factors, other error sources. I'm saying on this one, you know, do not use SEB, nonlinearity, or hysteresis, as they are not appropriate contributors when following the ASTM E74 standard. You're calibrating to a known standard, and they're just not applicable. Nonlinearity is the algebraic difference between the output of a specific load cell and the corresponding point on the straight line drawn between the outputs at minimum load and maximum load. It's normally expressed as percentage of full scale, commonly calculated at 40 to 60%. Now you have hysteresis, is the algebraic difference between output at a given load descending from the maximum load. And then you have static error band, which is the band of maximum deviations of the ascending and descending calibration points from a best fit line through zero output, which includes both the effects of nonlinearity and hysteresis. So if somebody says, I need SEB, hysteresis, and nonlinearity, and they're not doing an E74 cal, they should probably just use static error band. Hysteresis, putting both hysteresis and nonlinearity on top of it is going to be double dipping and seriously make the uncertainty much larger than it should be. But back to ASTM. So we have the lower limit factor. This is why we do not need nonlinearity or hysteresis. ASTM uses a method of least squares to fit a polynomial function to the data points. The standard deviation of all the deviations from the predicted values by the fit function versus the observed values is found by taking the square root of the sum of the squares of all the deviations divided by the number of samples minus the polynomial fit used minus 1. That's a big mouthful of what they're doing to understand it. So ASTM is, you're basically taking 30 or more points, you're taking 10 or 11 points along a range, and then you're rotating the device, taking another 10 or 11 points, rotating the device, taking another 10 or 11 points, and then you're taking the differences from the predicted values minus that, and that's this equation right here is the difference from those predicted values. And then you're multiplying that by 2.4. And then you're multiplying that times the average resolution. So you find the average resolution, you take the resolution per point. This calculation of lower limit factor includes uncertainty contribution due to reproducibility and deviation from the interpolation equation. The contributions due to the other uncertainty components present during the calibration should also be included. So if we're looking at that, that's what the lower limit factor is. We're taking all those points, we're drawing a curve. That curve, those predicted responses, negates nonlinearity. It negates hysteresis. If you're doing descending measurements, you should have the instrument calibrated in the descending fashion, but you do not need to include nonlin or hysteresis. So if we're looking at doing the Force CMC for ASTM E74 calibrations, what we're going to look at, we need a calibration report for the device, the uncertainty of the instruments that were used to perform the calibration history, which is going to give us stability, manufacturer specification, that's going to give us our environmentals, error sources if known. Most of them are not known, and a lot of them are adapters. So if you're listening to this, be sure when you have your instruments calibrated that you're having them calibrated with the same adapters they're being used with, because off the top of my head, I can tell you that half percent error is not uncommon from switching different hardness of top locks on compression load cells. So we've had other webinars dealing with that. And then the end user, you get all that stuff back, and then as the end user, you're going to have to conduct the following test: a repeatability study and R&R between technicians. And then most ABs are going to say, hey, where are your proficiency testing requirements? So you're going to eventually need to complete those, which that sheet has the EN ratio that can be used. So type A, so we're looking at that part 1, ASTM reduced to 1 standard deviation. I'm taking this from a report, standard deviation, resolution, lower limit factor, class A verified range of forces. This is one that the first test point was 50 pounds. When we look at this, if we're going to enter this into the Excel sheet, we're just going to enter 0.21 force units. The Excel sheet's going to divide it by 2.4, and it's going to equal 00875. So let's see what happens. So there, the highlighted portion is the Excel sheet. When we entered it into our the front page, we entered it in as the 2.4 divided. It was divided, and we got the 00875. So that's the first point. So if we're looking at uncertainty contributors and we're using that Excel sheet that I showed at the beginning of this, then we can reduce that. The next thing we're going to need to do is probably take repeatability of the best existing device. And if we look at the definition for the VIM, repeatability, condition of measurement, out of a set of conditions that includes the same measurement procedure, same operator, same measuring system, same operating conditions in same location, and replicate measurements on same or similar objects over a short period of time. And then you get measurement repeatability, measurement precision under a set of repeatability conditions of the measurement. So short period of time, we have a cal machine. We're going to use a load cell. We got our load cell calibrated by Morehouse. We're putting it in that Morehouse PCM, say, and now we need our best existing device. We're going to put another load cell in there, and then we're going to do repeatability studies on this other load cell, and we're going to do it throughout the range. Here, this example, we're just doing the 200 pounds. So we apply 200 pounds. Our best existing device that we can put in that machine is another shear web load cell. We get 200. We apply 200 pounds again, we get 199.99. We apply it again, we get 200.02. We apply it again, we get 200.01. This does 4 runs. This is pretty good. At least 3 runs should be done. You can do up to 10 runs, but this is pretty good. And then we're going to take our repeatability or precision is going to be the standard deviation of these four runs, average of 200.005, resolution, standard. The sheet's going to do it all, but we're going to be responsible for doing it. And the good rule would be to take a repeatability point, because we're going to want to do it for the full measuring range. Good rule would be to take a repeatability point for every 10% of the loading range. So if I have a loading range that is 10,000 pounds, I should take points at 1,000, 2,000, 3,000, 4,000. If I'm going to use it below 10,000 pounds, I may want to get a second load cell and do points at 100, 200, 300, 400, and so on up to 1,000. And that is a decision that people have to make. My recommendation is at least every 10% for every loading range that you're going to do. And yes, there can be overlap. So if you do 10,000 pounds and you have a 5,000 pound loading range, maybe you can do a 500 pound point and then 1,000 pounds. There's no exact science to how many points. It's just take enough that capture what's going on within that loading range. And then we're going to do something, this one's a bit more, reproducibility between operators. Now, A2LA R205 at the MAC, it's not everybody's getting reproducibility. People say it's difficult to calculate, to do it right. There's so many different ways to do reproducibility. The easiest way, I think, is if you have more than one operator, is to just take it between technicians. In this example, it's on the sheet. You can do an R&R. Reproducibility was determined using an R&R study. Each of 2 technicians performed 10 runs of data, the same point, and their overall results were compared against one another. A standard deviation of the average was calculated between technicians, converted to the appropriate units, and used for the final reproducibility number. So right here, you have this reproducibility between 2 operators is the standard deviation of the average. And if you look at it, it's highlighted. The average is relatively close between our 2 operators here. Repeatability, not as close, but the reproducibility between this and taking the standard deviation of the averages for both the operators was quite low, and that can satisfy the requirement. If we look at the VIM definition, reproducibility condition of measurement, condition of measurement out of a set of conditions that includes different locations, operators, measuring systems, and replicate measurements on the same or similar objects. So in our situation, and I assume many of you are in the same situation, if you have a force lab, you probably don't have many different locations. You probably have your one force lab. So different locations is it going to happen. We can do different operators, yes. We can either do different measuring systems if you have multiple machines. You can do it that. Replicate measurements on the same or similar objects. So I prefer to do it on the same objects. Sometimes it says similar objects because if you're testing a fuse and you blow the fuse, you cannot put the smoke back in. There's other things there too. But if we look at also MSA 4th edition, reproducibility, this is traditionally referred to as the between appraisers, variability. Reproducibility is typically defined as the variation in the average of the measurement made by different appraisers using the same measuring instrument when measuring the identical characteristic on the same part. So if we go by the MSA definition, which seems to be accepted by several people, that we can use reproducibility, we can satisfy that criteria by doing between operators. So if we look at that, we added, again, this sheet auto populates all of this. Since we only had 2 operators, if we looked at the repeatability between them, we only have 1 degree of freedom. But since they each operated reproducibility, each of them did 10 points, we have 18 degrees of freedom. And that's getting more into measurement uncertainty and what constitutes the degrees of freedom. So that's, if you're more interested in measurement uncertainty, I encourage you to take our 3.5-day or 4-day class. So now this has basically covered the type A. Now we can look at the type B criteria. Resolution of the best existing device, that's easy. Resolution is the smallest change in quantity being measured that causes a perceptible change in the corresponding indication. So if I have a device that's reading by 0.01 pounds and it's fluctuating by 0.02, 03, then maybe my resolution is actually somewhere like half that, 0.15 or 0.02. But if my device is nice and stable at the 5th decimal place, that's my and I can measure. I can, a sensitivity. I can measure. It can vary by 0.0001 millivolt, and I can touch it, and it's 0.001 millivolt, and it's nice and stable. That would be my resolution. And then best existing device. That's per ILAC P14. The term best existing device is understood as a device to be calibrated that is commercially or otherwise available for customers, even if it has special performance stability or has a long history of calibration. For force calibration, this is often a very stable load cell and indicator with enough resolution to observe difference in repeatability conditions. That's important. If you want to do a 100,000 pound range and a 10,000 pound range, you're probably not going to have enough resolution to do both ranges with a 100,000 pound load cell. So you're going to need 2, highly recommended, as it's going to be the resolution is going to be way too high. It's going to be very, very as far as the uncertainty contributors go, it's going to be a large portion of the uncertainty contribution. If you try to use a device without enough resolution, it's going to raise the budget quite a bit. So resolution of the unit under test, for us, this is for this example, when we did set up the second load cell, it was 0.01 force units. So smallest change in quantity, resolution of the reference, that's something that's on the calibration certificate. So we're using a load cell as a reference that was calibrated by deadweight standards, and then we're using a second load cell in our system to do the repeatability study. So we're going to have the resolution of both of these. So then you get to the reference standard uncertainty. This is usually the measurement uncertainty in the calibration of the reference standard used to calibrate the force measuring device. It is the uncertainty contribution in the calibration of the reference. So in this example, we're going to use our dead weight machine. It's because we calibrated the load cell 0016. So what we can do is we can examine the CMC and what the reference CMC does to calibration results, Morehouse versus a accredited cal supplier. When we did this, this is not this example. This is a 10,000 pound load cell. We calibrated it, used all these contributors. This is our 10,000 pound standard. Then we took it over and we did it in another machine, and things changed. Repeatability wasn't as good. And if we used secondary standard instead of primary standard, we got expanded uncertainty of 4.03 pounds instead of the 10. So what we saw is basically at capacity at 10,000 pounds, the calibration, the expanded uncertainty when calibrated with primary standards was approximately 10 times lower than if using secondary. So you find that on the CalCert. You can, think about that. Do I need dead weights? Do I need, can I live with secondary? That's decisions that need to be made. The lab performing the calibration with the device using deadweight primary standards with a CMC of 0016 applied. So there we get 0016, 200 force units. We're going to enter 0.0032, and then we're going to divide by the appropriate coverage factor. In this case, it's K equals 2. And we have the reference standard stability. This is the change in output from one calibration to another. This number is found by comparing multiple calibrations against one another over time. If the instrument is new, the suggestion is to contact the manufacturer for stability estimation on similar instruments. This should be any ASTM E74 report as the change from previous, and the exact value change from one calibration to the next should be used. So if you're looking at it's calculated. We recommend it per point. There are other ways to do it. But we recommended to compare the last cal versus the current cal and do it per point. If you have 20 years of history on the device, there are many other methods to do, but pretty much a lot of people, this method will work all the time. You do the last cal versus the current cal, put in the actual value, you'll get it throughout the loading range. And this one, it was about 0.01% that we entered in. Then we have environmental factors. Usually this is temperature on a load cell sheet if you're using a temperature other than what it was calibrated at. Our lab varies plus or minus 1 degree. Most force labs that I know, most people I talk to, are controlling the temperature fairly well. 1 degree Celsius is achievable, and you can find that on the manufacturer's spec sheet. If you want to convert it, you can use the Fahrenheit. If you want to work in that, we converted it to Celsius as that's what we're operating in. It's 0.0015 per 1 degree C. That's found on the sheet. So we put that in. We put that in our sheet. We type that into our sheet, and then we get 0.003 force units. So other error sources. In the example I put in a misalignment, and you can find that we have about, depending on what machine's being used as a transfer or comparator machine, about the worst is a 16th measured off center line. So I put that in, just an example of something else some people may consider if they're using our cal machines. They may want to put that in. From the specification sheet side, load cell sensitivity is 0.05%. I multiply that by the 1/16th of an inch. We get about 0.003. And then we're going to multiply that times the 200, so we get about 0.15 force units. Other error sources could include geometric alignment, timing, and contributors associated with using different indicators. If the device is calibrated with a different indicator than it was used for calibration. So then you have other things to consider if you're swapping indicators. NCSLI RP12 will tell you some of the things to use for indicators and amplifiers. We recommend you if you're using a reference standard load cell, buy a good indicator, keep them together married as a system. If you're interchanging meters, then you're going to have to do a whole nother uncertainty analysis on those meters and add that to your budget. So other error sources, there's lots of them. We cover these all in our 3.5-day class. Cable stiffness and mounting. using mass instead of force weights, misalignment. The mass instead of force, force is force anywhere in the world. It's already been corrected. Mass requires, depending what's being done, if you're doing a crane scale, using mass weights, it's going to require the correction for gravity. So that's dependent on what you're using, what needs done. Thread depth on a column load cell, loading through the bottom threads and compression, all these error sources, static calibrations versus dynamic use. There's a nice session that's going to be given by NIST on fundamentals of dynamic force metrology at NCSLI this year, 2018, August 29th in Portland, if anyone's going. That's session 5, and a very good presentation on dynamic force. Their molecule excitement decline, timing errors, flatness, adapters, difference in technicians, all kinds of different error sources. So that's basically it. You get all those. You enter them all into the sheet. What we went over. It's very easy when you have that sheet in front of you. It just walks you through everything. Enter them all in, and at the end, there's a 3-point cal. At the end, you can get your uncertainty per point. You can have an equation that you can put on. It'll give you the equation that you can put on your scope that you can calculate. As you can see in this example, at 200, we're at the highest, around 021, and then 400, 012, 2000, 005. So we use the Welch-Satherthwaite equation. There's some additional things to consider depending on who's listening to this topic. Using Welch-Satherthwaite with infinite degrees of freedom for type B may not represent the true uncertainty, as the coverage factor would increase without infinite degrees of freedom. But that's a debate. We're getting into the really nitty-gritty that certain people will want to debate. And what that does is raise your coverage factor. If you take away the degrees of freedom, you end up with a slightly higher coverage factor. If the other thing in this example, if we include repeatability between technicians, remember that first point was 021. If we stick repeatability back in, it becomes significant part of the contribution, 61%, which puts our expanded uncertainty to 07. That's another consideration if you're looking at your measurement process. In this scenario, between the two techs that we had numbers in class. I would prefer to use 2 trained technicians, and I would set up a test. If I was doing a true R&R, I would set up the test with the absolute best equipment. So other things to look at, it does give the bars here that show what the major sources of error are. If we use if we just looked at the 200 and 400 pound point, going through what we just did, plugging those numbers in. Of course, I didn't cover the repeatability. The next step obviously would be to do the same thing we just did, and put the repeatability information in for the 400 pound point. Now let's do 400 pounds 4 times and see what happens. Next point in the range, you can see the expanded uncertainty 02. It almost cuts in half at 20%. But the interesting thing here is this was with a reference standard that was 0.0016% of applied. If we change the reference standard to 0.025, we look at everything at the 400 pound point. The expanded uncertainty more than doubles, and then if I go back to that previous example, at capacity it can range from 5 to 10 times higher just by changing the expanded uncertainty. So from going from primary standards to secondary standards, the uncertainty will absolutely increase. The overall uncertainty, your CMC will get higher. Does that matter? It depends on what you're using your device to calibrate or your actual requirements. So if we do this, you have to do the next thing for each point in the range. But you know what? You've already entered all the information into the sheet. It's quite probable that only 3 things are going to change. So if you've done all this, you've done the reproducibility between operators and everything else, the repeatability of the best existing device, this will change as it is per point throughout the loading range. Reference standard uncertainty, this could change. If you're not using a constant like 0.016% of applied or using a formula, this would change. reference standard, stability, and that will change at each test point for the most part. If you're getting ASTM cows, you have a load cell, you send it in, we calibrate it, you get your change from previous back. That each test point, the stability of that cell is probably not going to be the same. So a lot of this came from a paper we wrote. We will be presenting that session 5 titled Uncertainty Propagation for Force Calibration Systems. We will be giving that at NCSLI this year. This basic paper just conduces that at tier 0, we can get 16 parts per million. At tier 1, we're looking at probably at around 0.02%. And then tier 2 would be if I want to do my go and do my CMC, I can get about 0.03%. So error, most of that, all that error was based on a 20% test point. 10% is usually going to be double, and then if it goes, higher to 30, 40, you can get less. And that's really what we're seeing. The tiers, that tier 0, 016, tier 1, tier 2, tier 3. Tier 3, we did this live and we traced it through with a deadweight cow, a calibrating machine cow, and we put another load cell in the calibrating machine and calibrated and just ran this down. So we look at this. The Morehouse / ASTM method that we were discussing today, primary standards dead weight, really the same if we compare it with Euromet, which is used international protocols, ISO 376 calibration. If we look at that difference, not much. Euromet's basically saying, hey, primary standards are generally 001 to 005. We're within that at 016. If we look at the comparator with 1 or 3 reference force transducers, this is where things change quite a bit using the ASTM method. We were able to obtain 0.2, and if you look around a lot of people's scopes, a lot of your scopes that are out there, you'll see things like 0.2, 0.5, very believable numbers. Now Euromet says, hey, the best you can get is 0.5. And there's a picture here from Euromet, comparator with 1 or 3 force, typical range, expanded relative uncertainty. They're saying they're at the here at the bottom, here, they're saying this. So comparator with 1 or 3 reference force transducers. Why is theirs higher than what we're getting? Well, when you're working with ISO 376, ISO 376 is taking more than the ASTM lower limit factor. It's classifying instruments based on reproducibility, repeatability, interpolation, 0. And then it's reversibility or creep, as well as the expanded uncertainty of the applied force. So we have this, and we really have this, where ASTM is not accounting for all of this. So by not accounting for all of that, yeah, I can believe this. This seems, unless we're going to start and switch to the ISO, completely to the ISO system, I can fully believe that from the tests that conducted, that 0.2% is a good number and is very achievable for most comparator systems, or most Morehouse comparator systems, when the load cells are calibrated in accordance with E74 and they are calibrated by primary standards. So all of that, if anybody wants to achieve 0.2%, which was what we did, we think it's, it seems very achievable if the right protocols are followed and the right methods. And it also accounts for all of this. So nonlinearity, hysteresis are not in it. ASTM lower limit factors in it. Everything the auditors should require are in there. Other error sources, you're going to need to quantify those, but that's it. So hopefully everyone has gained something from this. I encourage everyone to download that online. Get the PDF of this and download that CMC sheet. It is free. It's an Excel sheet. We spent lots of time developing it. It will walk you through things, and we can answer any questions as they come up. Upcoming, we're at NCSLI in Portland. We're going to do a T23 force calibration on Monday, August 27th at 8 a.m. And we're going to do a torque class on Monday And this year we're conducting live gauge R&Rs with digital torque wrenches. Those will be supplied by a torque wrench manufacturer called Digital. We're excited to have them contributing their products for live R&Rs for the torque event. Registration for either tutorial can be found at NCSLI site. They are filling up. I think the limit on each class is 40. We're not near the 40 limit. I think we're close to 20. So just if anybody wants to get signed up. And then we will be presenting a very condensed version of this presentation at session 5A on Wednesday. And the other presenter is Dynamic Force from NIST. Very excited to see and be a part of that presentation. So with that said, there's a chat window at the bottom. I will open up the mics. I will stop the recording. If anybody wants to go back and re-listen to this, at this point it will be stopped. We have the spreadsheet, makes it easy. We covered calculating CMC when using ASTM E74 if you want a copy, please email. We have a working draft on how to calculate CMC for other scenarios. If you're interested in that, please send me an email. Happy to send that out. And we have in-house training from October 2nd to 5th, where Dilip Shaw will be here. He's one of the authors of the Metrology Handbook. He will be here doing a much more thorough analysis on uncertainty, what goes into it, degrees of freedom, everything you can think about. He will be here with me October 2nd through 5th to discuss everything and answer any questions that people bring. People in this group have had the class. I highly recommend it. So with that, thank you for your time.